be going over LeetCode's Biweekly contest 112. As usual, there are 4 problems of increasing difficulty. Let's start with question number 1. Share the link in chat. So this is called check if strings can be made equal with operations, and it's the number 1 version. There is a number 2. So you are given 2 strings, S1 and S2, both of length 4. This is curious. The length is exactly 4, and they consist of lowercase English letters. You apply the following operation on any of the 2 strings any number of times. You choose any 2 indices, I and j, such that j minus I is 2, and then swap the 2 characters at those indices in the string. And you have to return, this is a decision problem, you have to return true if you can make the strings equal and false otherwise. We have a few examples. Okay, very small input. And in any case, let's think about it, because maybe we can reuse the solution for the question number 2, which is the second version of the problem. So the first thing we need to understand is get some intuition about this condition. So this means that for this to be true, so j has to be greater than I by exactly 2 positions. So that means that there are only 2 possibilities. So if I is 0, let's draw it out. So the second example is A, B, C, D, and so S1 is A, B, C, D, and S2 is D, A, C, B. So there are only two options. Either I and j must be 0 and 2, or I and j must be 1 and 3. So that means that this position, so these 2 positions, you can reorder, and these 2 positions you also can reorder between them, but they are independent. You cannot change anything within those groups, outside of the groups. So that means that in some sense the strings have to be equal in those positions. Equal in the sense of if you consider them as multiset of characters or counters of characters, they have to be the same. And if they are the same, you can order them to make them equal, and if they are not, you cannot. So let's code this. So like I said, I like to use a counter for comparing the multisets of characters. So for we have these two groups, and we are going to determine which group it is in terms of where it starts. It starts on 0 or it starts on 1. And then we want S1, we want the group that starts from start up till the end and jumps, the steps are 2. And this has to be equal to the same group in string number 2, but equal in the sense that we said that the counters must be equal. And this has to be true for both groups. So we use all. And this should be the solution. True, false. And there are no special cases here. I mean, in all these examples, the strings are multisets of this are equal multisets, the complete strings, but they don't have to be. But this is going to work anyways for those cases. So let's submit and accept it. Cool. So let's get to version number 2. And so this is the same problem. They should clarify this. I think that in Codeforces they usually tell you. They make you read it all. But I think the only difference here is this, that instead of the different, well, on the one hand, the length is n, which grows from 1 to 10 to the 5 inclusive. The difference is that this means that this is similar. We are classifying. So if you think about the strings in this way, this is position 1, 2, 0, 1, 2, and so on up to n-1. Then, so you can make swaps between all the even positions. For example, this 2 or this, well, this goes to 0. So you can sort it as you wish between the even, but then the odd are independent. You can only make swaps between the odd positions because the difference of the odds is always even. And so, I mean, it's the same as the previous problem, but instead of restricting to position 0 and position 2, for example, here, we extend that, the group, we extend it to all the even positions. So yeah, let's just copy paste this. Let's just copy paste it. So we did not assume the size here. So this should work. Hey, smart coder, how are you? So it works as it is. Cool. So it's a one-liner. Another option is to, instead of use a counter, you can sort. It's a similar thing. accepted. So it's the same. You are representing the multi-set of characters in a canonical way by sorting the characters and then comparing by equality. So it must work. All right, let's move on to problem number 3. Maximum sum of almost unique subarray. You are given an integer arrays nums, 2 positive integers m and k. Return the maximum sum out of all almost unique. We don't know what this means, but let's wait a minute. Subarrays of length k of nums. If no such subarray exists, return 0. Subarray of nums is almost unique if it contains at least m distinct elements. Okay. And then they define what the subarray is. It's non-empty. We already know what it is. And the maximum length is 20,000. The values are up to 10 to the 9, all positive. And we have this inequality here. Which makes sense because you cannot have more than k distinct elements in a window of size k. So yeah, this is a very common problem, and whenever you have a window of a fixed size, k in this case, I think it's much easier. People associate this with a sliding window technique, but there is a difference when the window changes size and when it doesn't. There's a big difference. When it's fixed, it's the code is much easier. You just keep moving the window one position at a time, which means that you add one element to the right side and you remove one element on the left side, and you keep track of some information of the window. In this case, we care about the sum and we care about the unique elements, the number of unique elements. Those are the two variables that we want to maintain. And we want to maintain them when we add one and we remove one. They rephrased the problem. They said m this pairwise distinct during the contest. Yeah. List m distinct. Yeah, the pairwise sometimes is a bit technical. What does it mean here? Pairwise distinct? Yeah. Yeah, I'm not sure what that word, what was the value of that word, but I think this makes sense. Like if you consider the size of the set of those elements, then it's that's the number of distinct elements. So, like I said, the key here is that we want to compute the sum and the number of unique elements quickly without going over all the window, the size of the window, because that would be quadratic, and this is too big for a quadratic algorithm. So, how do we do that? How do we compute that quickly. So we want to go over the array. Let's say that we are at position I, and we want to keep track of two things. On the one hand, we want to have a counter that tells us, so for value I, there are, I don't know, 3 occurrences, and for value 2, there's only 1, and so on. So why do we need this? It's because, let's call this the C. So the size of C, we know that has to be less, no, it's greater than or equal to M to satisfy the condition. And then we need the sum we need the sum to update our maximum. Okay, so if we are at position I, and let's say that this is size K, this is our window. So that means that we care about these 2 positions. This is position I minus K, right? Because this is the first element outside of the window. If K was 1, then I minus K would be I minus 1, so it makes sense because we only have 1 element. And then this other position is also important, which is I minus K plus 1. Why are those positions important? Because if we have the window for here for I minus 1 and we want to move it one place, then we need to add this element here, and then we want to remove this element here. Okay. Notice that this element could be, the I minus K could be outside of the array, and in that case we ignore it because we haven't yet completed the window, or we have completed it but we are not including, we hadn't completed it in the previous iteration. And then when we want to check if the window is complete, we check if this element is greater than or equals 0. That would mean that we have a complete window, and that would mean that we want to check the condition, and if the condition is met, we want to update the maximum. So with that analysis, the code becomes very, very simple. So we want a counter, we want the sum, let's call it current, cur of current, or if you prefer, and then we want to keep track of the maximum. It said that we return 0 if there's no such arrays. That's why we can initialize it to 0. And then we go over the array index I, and so we want to add, like we said, we want to add the ith element to the window. So that means we need to do two things. One is to update the count for that value. And then two, we add that value to the current sum. But then we want to remove the element that we are removing, that is to the left of the window. And we said that that index was here, we had it, was I minus k. So I minus k should have the element that we are removing, but there could be none. So we make sure that it's greater than 0. And now we remove. So we remove by subtracting this. And here there is a catch, because counters in Python, if we subtract 1 from this nums I minus k, it won't remove it. This is internally, it is a dictionary, and it won't remove it. It will change the value to 0, but it will keep an entry for this value, for this key. So we need to be careful with that. So because we want to ask this, we want to know how many unique values there are, and if we keep values that have, if we keep keys that have value 0, then we're gonna mess up the size. We're gonna get a bigger size than it really should be. So we first subtract 0 and we check if the count is we subtract 1, we check if it's 0, and in that case we delete it. So this is something of Python. In other libraries it should be different. Hello, Ralo Gomez. So yes, so now we have updated our information for the window, for the current window. So now we want to check first if we have completed a window. We said that this was the index of the first element of the window. We want to make sure that that is greater than delete. Oh yes, you are right. Yeah, so I forgot about this. So I usually prefer to do this on a function. Like we have a counter and a key, and we want to subtract 1, then check if this is 0, and in that case we delete it. Because I think this is the way it should work. I think that's clearer. Anyways, so thanks for the pointer. So first we check if we have a complete window, and for that we check the index of the first element must be greater than or equal to 0, and then we check that the condition is met, which is this: the size of the counter is the number of unique elements in the window, and it says that it must be greater than, it must be at least m. So we have a candidate window, so now we update the sum, which we stored in current, and that is it. Pretty straightforward if you ask me. Count. Yeah. So we get the examples right and accepted. Cool. So yes, I think it's you should not mistake this problem with the two-pointer or the sliding window where you have to grow it and shrink it and the size changes. That's more complicated. These problems they always have this structure where you add one element to the right, then you conditionally remove, if there is one, you remove the element to the left. And then if you have a complete window, you have a candidate and you do something, you update a maximum or so on. There are many variants. Sometimes there's a classic problem where you need to get the medium, so you can store the window in a sorted list, for example, and get this kth smallest element. Fix sliding window. Yeah, that's a good name. Just make sure you distinguish because there are very different type of problems. Okay, and I like this because I feel that this is the way the counter should work. So I like to encapsulate that kind of operations and makes the code cleaner, I think. All right, so let's see. So let me share the solutions. So I'm gonna share Q2. Q3. And, well, maybe Q1 as well, even though it's the same. Just for completeness. And now the hard one. All right, so you are given a string s and an integer k, and a k subsequence is a subsequence of s having length k, and all these characters are unique, okay? Every character occurs once. So here, subsequence, remember that it's not necessarily contiguous. You get the definition here, but it's very standard. So they define this function, which is the number of times a character occurs in the whole string. And the beauty of a k subsequence is the sum of the occurrences of every character. Remember that every character must be unique. And here we're given an example. We get two examples here. Okay, so the length is 200,000 at most. And yeah, right off the bat, notice that k, it could be that there is none in the case that k is greater than the unique characters in S. So and another observation is that the order doesn't matter in the original string because these subsets are essentially these subsequences are essentially subsets of size k. So a subset, it doesn't matter where the characters are. It's just you just choose to add one or not, etc. So we can represent this as this function as a counter. And if k is greater than the length of the counter, then there are 0 k subsequences without even checking for the max beauty. All right, so let's see. We have maybe we can work out an example. Yes, so this one, A, B, B, C, D. And then k equals 4. So here, so like we said, the order doesn't matter. So we can represent this as a counter where we have A occurs 1 time, B occurs 2 times, and C occurs once, and D occurs. So let's call this F, because that's how the problem statement called it. So you can think about these numbers, even though it's the number of occurrences, they define it as a score or a value. And so here B has the highest score. Okay, so we don't really care about the character. We only care about the scores, right? So if we choose, so if we want to know what the maximum score is, we can sort them in terms of their value. So in this case, it would be 2, 1, 1, and 1. And we want a subsequence of size 4. So we are going to take all of it. Okay, so the max score, or max beauty as they call it, let's call it score instead of beauty, is the sum of this, which is 5. Yeah, I don't know if this is the clearest example to illustrate this. So there are 2. The answer is 2 because B has 2 occurrences, so we could choose one B or the other B. We are going to choose at least one B because it has the maximum score, and we're going to choose all of the characters here because K is the same as the number of unique characters. That's why I'm saying that maybe this is not the best example to illustrate the solution. Is that an example that you worked out? So let's work out this one. BCCA and K equals 2. Got you, TLE. Okay, we can try it out. No, it was 2, right? And the answer was 4. That was the best contest. Biweekly 360. See, yes, that's one of the... that's a very growth mindset comment, if you think that was... What do you mean by reap? By the event rated or something like that? Anyway, so let's work out F for this. So we have A occurs once, B occurs once, and C occurs twice. And again, so if we sort them by value in reverse, we get this. But in this case, we need to choose 4. We need to choose 2. So it doesn't matter how many, like I said, the characters, we only care about their scores. Okay, so here the maximum score is going to be 3, because we're always going to take a C, because the value is greater, is the greatest, and then we are going to take one of the ones. But since the counts are the only thing that matters, we can count again how many times each score occurs. So this is usually called the count of counts. So let's call it, let's write it down. So here we have 1, 2, and 2. Well, the 2 occurs 1 time. This is sometimes confusing. And the 1 occurs 2 times. And like we said, we want to go in order. These are the scores, right? Remember, these are the scores, and this is how many we have of scores. So we can do this greedily. The one with the greatest score and so on until we can't take anymore because we have taken K. So that is the idea of the solution, essentially. So it's you don't need the P, you don't need to make, you can do it greedily. So let's say that the score, we're gonna go over the score and the, how did we call this? The how many we have of that score. And we want the counter of the value. We only care about the values, like we said, and we want to count. We want a counter of the value. So this is going to be a score and a value, but we want them sorted. So we want them sorted. So these are the items from highest score, sorted from highest score to lowest score. Okay, so how many can we take? Well, or let's call it take. How many can we take? We can take the minimum between what we have and k, which is the limit. Okay, and at the end we're gonna subtract from k how many we took. We are going to keep track of the count, the variable res, and now we have to count in how many ways we can take elements with score. So that is, yeah, this is a multiplication, okay? Because at every point we make a decision that is independent from the next decisions. So we want to multiply them, because for every combination of taking this scores, the elements that have the given score, we can change. We can combine them with all the combinations of the following scores. So that's why it's a multiplication. So let's remember that we need to mod this. And here, how do we do this? So we want to count how many ways there are to choose to take from have. Okay, this is the Python already has a library function in math that does the choose, that computes the choose numbers, the combinatoric number. We're gonna leverage that. It doesn't matter that it's not modded, because these numbers are pretty relatively small, because they are they can be at most 26 if I'm not mistaken, because it's the number of occurrences of yes, it is a number of unique letters. So these are the ways to choose take from have. Notice that in the first iterations we probably can take all that we have, and in that case have and take are going to be the same, and then there's only one way to take n from n. But then we're multiplying by the score count times, take times. But we want to do this mod, so we use the pow function in Python. And then finally we mod the product, and then we mod the result of this multiplication. So I think this should be it. Count is not defined. Where did I? Yeah, this is F. 4 and 2 and accepted. All right, so yes, I mean it was a surprise. My first solution used yeah, No, to be I'm not gonna lie. My first solution used dynamic programming, but then I thought about it a little more and I realized that it wasn't necessary. So yes, it took me a while to solve this one in the contest. The math, yes. So, I mean, I'm not gonna dive into what the combination, how to compute the combinations. I can do that in another stream, but let's assume that we have this given and we can discount in how many ways we can take from have. And so if you, so do you understand this part that we have this many ways, we have to choose less. If we have to choose less than we have, then these are all the ways to choose. And then yes, so the score are the number of occurrences of each. We choose a combination of the characters that have this score, and then for each we have score occurrences. So we can choose any of their occurrences. Yes. This is a little tricky. That's why I'm trying to. So yeah, let me do it in the board. So here we have the counts of the counts. So this is what we call the scores. But remember, even though they are scores, they are also the number of occurrences, right? Because here this 2 means that there were 2 C's, and these ones means that there was 1 of A and 1 of B. So now when we are iterating, let's say that we are considering this one. So here at the first iteration, we had only one 2. So in that case, so let me first consider this one and then the other one. So we have only 1 2, and we have to take 2, so we can't take them all because they have the highest score. We want to take as many as we can. So we are going to take 1 2, which means that we are going to take 1 C. If you go back to what it means. So we have choose want to choose from 1, 1, because only C has scored 2, and this is equal to 1. But we can choose each one of the C's, this one or this one. So let's say that they have sub-indices. So this is, the subsequence is different if we choose C1 or if we choose C2. And this is reflected by this number. So that's why we are multiplying by 2 here. Okay, which is what we... so we are multiplying by 2 to the 1 because we are only taking 1 in this step. And then when we go to step 2, now k is 1 and we have 2. So we want the ways of choosing 1 from 2, which is 2. And what does that mean in terms of the string? It means that there were 2 which scored 1. So we can either choose the A or the B. That's why what this is counting. And then the value is 1, so the score is 1. It doesn't matter if it's an A or a B. The number of occurrences was 1. And we are choosing 1. So, okay, so this is not the best example, but I think that if you do this mapping from here, I'm not going to lie, it's tricky to follow sometimes this count of counts. There's a lot of indirection. So it's useful to go back. So from here to here and here, this is becoming a mess, but so we are translating this into this. Here we don't lose information because the order doesn't matter, as we said. But here we do lose some information, but that information is irrelevant to solve the problem, as we proved by solving it. But it's useful to go back to this to interpret this formula. So I don't know if that clarified it completely, but I guess it helped. I did not prepare a better example. I guess the ideal would be to have an example that is small enough to work out in the whiteboard, but that is a little more complex. So we can see here, so different values here, because here the exponents are always 1. Okay, yeah, I mean, rewatch it, or you can ask more specific questions in the Discord server. All the feedback and questions are welcomed. But let me try again with the exponent here. Is because, yeah, you can plug it in if you'd like. So again, here we are choosing between, so the B and the A have the same score or the same number of occurrences, but if they had more occurrences, let's say that there were 3 Bs and 3 As, then they will end up in the same item here, which is that the score 3 has 2 occurrences. And again, we would choose 2. We would choose but here we would have 3 options for the B and 3 options for the A. So that would mean that this would be 3 to 3 squared, like we said, because we have 3 options and 3 options. If we were choosing 2. So yeah, I don't know if this is clarifying, but yeah, let me know if you have any questions. I'll answer them afterwards, or you can comment on my videos. So yeah, but I think this solution is the simplest one that I could think of, and I think it's pretty efficient. Then the Q1 and Q2, I think these one-liners are as simple as they get. And this one, I think it's a very standard problem, and it's an easy medium if you already know if you've done this technique before. So yeah, that's all I have for now. Thanks for watching, and see you in the next one.